Hello, this is for section 8.3, inference for two or more groups. The first test we're going to talk about is when we're testing two or more proportions. So this is the categorical analog to the ANOVA test. And sometimes this is called the test for homogeneity. Basically testing if everything is equal to each other. So we still need simple random samples. Independent samples. And all expected outcomes must be at least 5. So greater than or equal to 5. The hypotheses for this are, well, the null hypothesis is that all the proportions are equal to each other in however many proportions you're talking about. The alternative hypothesis is that at least one proportion is different. Okay, so when you're doing these types of problems, you'll either be given the contingency table or they'll give it into you paragraph form and you'll make the contingency table. And this is just an example of what one might look like with 3 samples and we're keeping track of 2 categories. The 011 is saying the observed value for sample 1, category 1. The observed value for category 1, sample 2, observed value of category 1, sample 3, and then most of the time you actually have to calculate the totals, but that's just adding up across the rows or adding up across the columns. So that's the given information. Now all the expected outcomes must be greater than or equal to 5. That's what we need to calculate. So for each observed value, you will have to calculate one expected value. That's why these tables are the same size. And how you calculate the expected value for a certain entry is you take that row total times the column total and divide it by the grand total. And then after you calculate these expected values, to calculate the test statistic, you take each observed value minus its expected value squared divided by its expected value. And now since we're keeping track of rows and columns, that's why we have the double sigma sign here, because you have to take the double sum. And then this is chi-squared. And just like the t-distribution, this does have a degrees of freedom, but it's not n minus 1. It's the number of rows minus 1 times the number of columns minus 1. So that's R is the number of rows, C is the number of columns, subtract 1 from each, and multiply them. Now this chi-squared distribution comes from squaring a t-distribution. So when you square the negative values, they become positive. So just like the F distribution, you're going to get a right skewed distribution that only has positive values. And then also, just like ANOVA, because we want to test whether this is bigger than expected, because if the observed values are close to the expected values, this will be a small number. If the observed values are far away from the expected values, this will be a large number. So we're looking for large numbers to reject the null hypothesis. So this is always right-tailed. So like I said, this is a chi distribution. Chi-square distribution. Which implies when you do the critical value method, you will use Q chi square. It's just SQ. Q chi SQ. And then the p-value method, you'll use P chi skew if you're doing it by hand. But very similarly to ANOVA, we can almost always use the R functions for these problems. And it's the chi-square dot test. And the only input there is you have to input the data, but it has to be a matrix. So when we do the first example, I'll show you how to type in matrix in R. So example 1. A psychologist is interested in testing whether there is a difference in the distribution of personality types for business majors and social science majors. Test at a 0.05% level of significance. So let's go through the requirements. Simple random sample. Yes. Independent. So our business majors and social science majors, do they influence each other? No, they do not. So they're independent. But now, greater than or equal to 5. We have to check the expected outcomes, and we have to do that in R. So I'm going to go over to R real quick. The first thing I want to do is type this in as a matrix. So I'm just going to call it person for personality. Oh, never mind, that's a test. So I guess I'll spell out personality equals matrix. And then you go collection, just the C parentheses, and type your values in. Now you can either go left to right or up and down. I'm going left to right. So now I typed in both rows or all the columns. You then tell it the number of rows. We had 2 rows. And you tell it the number of columns. We had 1, 2, 3, 4, 5 columns. And then you just have to say by row. By row equals. Now I went left to right, so by row will be true. If you went up and down, then by row would be false. Now let's just kind of look at what this is. So you notice, and I recommend doing this part where you look at the matrix and make sure it matches the table you have in the problem. There, I match. So now to get the expected values, we're going to go chi square dot test personality, and then $sign outside of the parentheses, and then expected. So that gives me the expected values for this problem. Are all these numbers at least 5? Yes, they're all at least 5. So let me go ahead and copy this. So I can paste it over here. And then I'll go back to the notes. So there, our size requirement checks out. So now we are ready to do the test. So we are doing the test for homogeneity. So what is the claim? The claim is testing whether there is a difference. So the claim is there is a difference. The opposite of that then would be that they're all the same. Now, the thing I'm keeping track of are the personality types. So the proportion of open personalities is equal to the proportion of conscientious personalities, is equal to the proportion of extrovert personalities, is equal to the proportion of agreeable personalities, and is equal to the proportion of neurotic personalities. So we actually have 5 proportions we're testing in this problem. Okay. And then the null, well, is where they're all equal. And the alternative is that at least one is different, or there is a difference. And then, as we've said before, this is a chi-squared distribution, and it's always right-tailed. What is our significance level? I don't believe we were given one. Let me go back up. Oh, we were given one. 5%. Good. So 0.05. And now we're ready to calculate the test statistic. So this is where I'm going back to R. And now I'm just going to go chi-square dot test of personality. But this time I'm not going to do the $ expected. I'm going to leave that off. And it does the chi-squared test for us. And notice it gives us an x squared value like the 2 prop and 1 prop test did. But this time, since we are doing a chi-squared distribution, we want the squared value. So our chi-squared is 3.006. You do not need to take the square root. Our p-value and our degrees of freedom. So let me copy that. And go back to the notes. So our test statistic chi-squared is 3.006, like I said. The p-value is equal to 0.5568. The degrees of freedom, just, I know it's 4 because it's telling us in the code. But remember, it's the number of rows, so 2 minus 1 times the number of columns minus 1. So that would be 1 times 4, so 4. Just to double check that R is calculating correctly. So now, because I have the p-value already, I'm going to go the p-value, well, is greater than or equal to, it's greater than alpha. So that implies we fail to reject the null hypothesis and fail to support the alternative hypothesis. But our conclusion should always be written in terms of the claim, not the hypotheses. So now I'm going to go back up. Our claim, well, that matches the alternative. So I fail to support the claim. So there is not enough evidence to support the claim that there is a difference in personality traits between I need to go back up. I forgot. Business and social science. Business and social science majors. At the 0.05 significance level. There's example 1. Example 2. A public health researcher wants to examine if different exercise programs, yoga, aerobics, and strength training, have different impacts on blood pressure categories in patients. Test at a 2% level of significance. So simple random sample. Yep. Do we have independence? Yes, because we're assuming that since we're testing different exercise programs that there's no overlap. But then the size requirement, or the greater than or equal to 5, we have to go to R to do that. Let me go over to R, erase the last problem. This time I'm going to go exercise equals matrix. I need to put my data in first. So collection. Then I'm going left to right again. Number of rows equals 3. Number of columns. Oh. Notice how I put an S on row. That would have given me an error. N row equals 3. N col equals 4. And by row, because I went left to right, equals true. I just realized I left the E off exercise. That's fine. And now I'm going, let's look at it, make sure that I typed everything in correct. Everything looks good. And now, square.test exercise. And then don't forget the $ expected. So this will give me my expected values. Are these all at least 5? Yes, they are. So let me copy that. Over to the notes. Oh, something went wrong. Let me try again. There we go. And back to the notes. So, we meet the size requirements. So now I'm going to do the test for homogeneity. I feel like I'm spelling it different every time. I'm not the best at remembering how to spell that word. But okay, so what's our claim this time? The claim has different impacts. So the claim is that at least one is different. So then the null hypothesis is that P1 equals P2 equals P3 equals P4, because we have 4 columns. Oh, sorry, I meant to call that the opposite, skipping a step. But the null hypothesis is also equal to that. And then the alternative hypothesis is that at least one is different. It's a chi-squared test, so it's right skewed. It's also a right-tailed test, and our significance level is 0.02. So now I need to calculate the test statistic, so I'm going to go back over to R. Now I'm just going to go chi-square test of exercise, but no $ expected. And there we go. Got a chi-squared value of 38.218 and a p-value of basically 0. Okay, back over to the notes. Paste that in. So again, our chi-squared value is the 38.218. Degrees of freedom is 6. I'm not going to double check that. That's time. And the p-value is basically 0. So this time, the p-value is less than alpha. So we reject the null and support the alternative. So if we were doing an ANOVA test, we would then go on and do a pairwise t-test. Now we could do a pairwise chi-squared test here and do the Bonferroni correction where you calculate that alpha star that you saw in the previous project. We're not going to do that this time. What we're going to do is just compare what we're seeing. So what we're trying to compare is the observed values, so right here, to the expected values and see which one seems further off than the rest. So we got 45, 65, that's about 20 off. That's a little over 17 off. Those are a little over 13 off. The rest all looks less than 10 away, though. Oh no, I guess I missed this one. That's about 12 off. I'm not going to include that. So notice how he said 10, 12, and kind of waffling back and forth. Some people might not even consider 13 too far of a distance. This is very subjective, but one thing you can do is you can take the total sum of it, so add up all the numbers. And when we do that, we get 475, so that means our grand total, or N, is equal to 475, and take about 5% of that. And 5% is a completely objective number. We're looking basically, though, to be the most common alpha values. So about 23.75. So things that are 23 or further away, which I guess would only make the 45 and 65 matter this time. But like I said, it's subjective. That's just a rule of thumb. You don't have to be exactly that. And you just explain that. So let's look at what did those represent. So it does look like yoga and aerobics tend to have a higher proportion, or no, yoga has a higher proportion of normal blood pressure and a lower proportion of hypertension stage 2. And aerobics seems to have a higher proportion of normal. Lower, I meant lower. So how am I getting that? Well, so for yoga, I expect it to be 45. but it was actually 65. That's why I said higher. And then this, I expected to be around 18, but it was actually 5, so that's why I said lower. I expect this to be 52, but that was 35. That's also why I would set lower. So all of this is going to play into our conclusion. So the conclusion is, oh yeah, which one did it match? Our claim matched the alternative, so we support the claim. So there is enough evidence to support the claim that um, the type of exercise produces different proportions of blood pressures. In particular, yoga has a higher proportion of normal blood pressure and a lower proportion of hypertension type 2. I'm abbreviating there because I'm running out of room. Also, aerobics has a lower proportion of normal blood pressure. And that's it for example 2. I'm going to be making one more video to talk about the testing for independence.